All right, we are in section 3.4. Yes, this actually does go with our limits unit. And right here, we're talking about limits at infinity, or also known as horizontal asymptotes, which you have dealt with before. So we're basically going to figure out how do we evaluate limits at infinity and what does it really mean? So first of all, let's talk about this thing which is called ending behavior of a function. So what is ending behavior of a function? So if we think about a function, whatever it looks like, and I'm not really going to draw a function here, but if we think about a function, we're really talking about what is happening with this function as the x values get very, very, very large. So as x goes really, really far that way, or as x gets extremely small, meaning it goes really, really far in that direction. So it is so big in both directions that usually it's so far off the graph we can't even like comprehend and can't really see it on the graph. We'll tend to draw things so that we can kind of get a good visual of them on the graph, but it's really what is happening at the ends. What is happening, or how does f of x behave as x approaches positive or negative infinity? So that's what we're talking about, is how does f of x behave as x approaches either positive or negative infinity. So we talk about the extremes. We talk about the farthest to the right that you can go and the farthest to the left that you can go on your graphs. What is happening to the function as x approaches those values? So we're just going to kind of do a quick little review. Earlier in the year, we determined the location of a vertical asymptote. Something like the function x over x minus 3. We know from pre-calculus that we have a vertical asymptote at x equals 3. And we know that because it makes the denominator 0 while not making the numerator 0. To show it using calculus, we use the concept of limits. So the limit as x approaches 3 from the right-hand side. So the reason I'm doing this is I'm bringing up something which is called sign analysis. We're actually going to analyze the signs, not as in like the sine trig function. We're going to analyze the positive and negative signs. So hopefully you can figure this out. If we took a number that is approaching 3 from the right-hand side of 3. Now remember, we want that number to be really, really close to 3. So we're getting really super close to 3. So like if I said, oh, 4. Well, 4 might work, but it's also not very close to 3 in the scheme of really close numbers. So you might think to yourself, oh, what if I do 3.000000001? Well, that's a much better number to use. Here's the thing. I don't want to have to worry about what all those values are going to be. All I really want to know is, we know from pre-calculus this is going to be a vertical asymptote. As an x value approaches a vertical asymptote, it really only has one of two choices. It's either going to go up to infinity or it's going to go down to negative infinity, because it can't hit the vertical asymptote. It can't go through it for sure. So, whoops. So all we're going to do is we're going to analyze the signs. So if I were to take something like 3.000000001, I'm not going to write that many zeros, but if I was to plug in, like, I'm not even going to write it, but if you were to put 3.0000001 in the x value on top, that's going to give you a positive value. If I was to plug 3.000000001 into the denominator, it's going to be a number which is just slightly bigger than 3, subtracting 3, so we're going to get another positive value out of it. So what we get is we get a positive over a positive, which means that this thing has to approach positive infinity. Whoops. All kinds of issues going on right here. What is going on? Go away. Thank you. All right. We're going to do exactly the same thing now as we approach 3 from the left side of 3. So now be careful here, because a lot of people mix this one up. If I plug a number just to the left of 3, like 2.99999, if I plug that in the numerator, 2.99999 is still positive. And then I'm going to plug it in my denominator. So now I've got 2.99999 minus 3. Well, that's a number just smaller than 3 that's subtracting 3. So it's going to give me a very small negative number, but it will be negative. which means a positive divided by a negative is going to be a very large negative number in this case, so it's going to be towards negative infinity. And as a matter of fact, if we were to sketch what this graph looks like, if you remember from our transformations of graphs that we did in pre-calculus type stuff, if we put 3 right here, here's our vertical asymptote. This is really just some kind of a shift of a graph, which is going to look something like this on this side, and it's going to look something like this on this side, and that's just a very, very rough sketch. But all we did was we kind of shifted a graph that would normally have been at the origin where that would happen, shifted it right 3 units. But as you can see, as you approach from the left, it goes to negative infinity. Approaching from the right goes to positive infinity. So we know that the limit here doesn't exist because they both go in different directions. And since they both approach infinities, we can't say that it goes to infinity or negative infinity. We just say that it doesn't exist, and it's due to unbounded behavior. It is unbounded from either side in this case. Therefore, since we get limits which don't exist in the unbounded behavior direction, x equals 3 is a vertical asymptote. Okay, so again, we knew that already, but if we actually wanted to show it, you would show that the limits approach an infinity, then you can say it's a vertical asymptote. Okay, long way to go to get there, but I want to show you how that ties into the horizontal asymptote idea. So we're going to go ahead and look at the next page. So if we remember that our rules from pre-calculus, we're going to let n of x equal the degree of the numerator and d of x equal the degree of the denominator. So if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So why is that? Now, let's just consider what we know about fractions. Typically, if the numerator of a fraction keeps getting bigger while the denominator stays constant, if you did we'll just make it easy. If we did 4 over 2, well, we know that's 2. Let's make the numerator bigger. Let's make it 8 over 2. Well, now it simplifies to 4. What if we make it 30 over 2? Now it simplifies to 15. So the numerator is getting bigger, and the denominator staying relatively small comparatively, so that means the entire function just keeps getting bigger and bigger and bigger, or the y values keep getting bigger and bigger. So really what's happening is the graph is going off to infinity. So it's doing something like this. It's just going to keep going that way, which means that there is no horizontal asymptote. It's not approaching any y value at all. So our example is like x to the 4th over x plus 1. You can clearly see the degree on the numerator is greater than the degree on the denominator. And it's really easy to tell that the fraction is going to get bigger and bigger and bigger the greater the x values that we plug in. All right, I'm actually going to skip the middle one. We'll come back to that in a second. Let's flip it. Let's say that the degree of the numerator is now less than the denominator, or the denominator has the greater degree. Well, again, think about what we know about fractions. Let's just say that we make the numerator 1. If I make it 1 over 10, it's 1/10. If I make it 1 over 1,000, it's 1,000th. If I make it 1 over 1,000,000, it's 1,000,000th. So basically what's happening is that denominator is getting really, really big, but the numerator is staying really small. So this thing is going to start to approach a really, really, really tiny value, but it doesn't go negative. It stays positive, so it's going to approach 0. So if the degree of the denominator is the bigger degree, it will always approach, y equals 0. Always. Now let's move back up to the middle one. This is kind of the special one. If the 2 degrees are the same, then this is what you do. Basically, these terms right here don't really mean anything as the numbers get really, really, really large. And this is where concept plays in. Because you're like, well, if I multiply 3 times a number plus 5, it's going to make a difference. It will make a difference the smaller the numbers are, but you got to imagine that these numbers are getting so incredibly large, like in the billions, trillions, gazillions, whatever they are, that adding 2 and adding 5 isn't going to do anything really to the ultimate result. It's going to be so minute, it won't really make a difference. So you're only looking at the highest power terms. So really what happens here is because we're looking at the highest power terms, the leading coefficients here are what becomes the horizontal asymptote. So it's just going to end up being y equals 5/12. That is actually what this function would approach, because it's really the multiple of the highest power terms that's going to give you the horizontal asymptote. Okay, now this is really like I said, this is really the pre-calculus way of figuring out horizontals. What I want to focus on is, we said the degree of the numerator and the degree of the denominator. I really want you guys to start thinking of this as not just the degree, because these are not always going to be polynomials that we're dealing with. I want you to think of this in terms of growth rate, because we're going to start dealing with other types of functions where you have to understand, oh, the growth rate of this function is greater than the growth rate of this function, which means, and then we'll get to, how it all plays out. So we really do need to start understanding different growth rates of different functions. In this case, these were all polynomials, and that's generally the way we learn this in pre-calculus. All right, so using the definition of a horizontal asymptote requires us to evaluate limits as x approaches infinity. So this is where the limit idea comes in. So the actual definition is that the line y equals L, a horizontal line, is going to be a horizontal asymptote of the curve y equals f of x if either one of the two things are true. Either the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. And remember, L is just some y value. It's a number. Okay, it's got to be an actual number. It cannot be infinity. It's got to be a finite value. So basically, as the limit goes to infinity or negative infinity of our function, if we get an actual number, we have a horizontal asymptote there. That's exactly what that's saying. All right, so let's go ahead and we're going to kind of examine again why this works. I've kind of already gone over this example with you just a little bit a few seconds ago, but I want to show it to you in actual numerical terms that hopefully will help make sense. Let's think about the function y equals 1 over x. When x equals 100, the y value is, if we plug 100 in, you get 1 over 100. Okay, nothing big there. But that is actually said mathematically, because we always say 1 over 100, it's actually said 1/100th, which if you put that in terms of decimals, 1/100th is 0.01. That is also said 1/100th because the 1 is in the hundredth spot. Well, what if I now put a million in for x? I now get 1 over 1 million, which is a bunch of zeros, which is said 1/1,000,000th. And that's actually going to be, let's see, tenths, hundredths, thousandths, 10,000ths, 100,000ths, 1,000,000ths. So it's 5 zeros after the decimal point. As you can see, you're getting a bunch more zeros. Well, if I keep putting larger and larger and larger numbers in for x, which is what it's asking us to do here, the number of zeros after the decimal place before you get to a 1 is going to get so incredibly large. And again, you have to understand, this is billions and trillions of zeros. It's going to get so incredibly large that this is going to approach 0. It will never actually get to 0, but it will approach 0, because you're going to have 0.00000 billions and billions of times, and then a 1 at the end. And then as you approach infinity, that just keeps on going. So the limit of 1 over x as x goes to infinity is 0. That's a really, really important concept. So there's a theorem that says that as long as r is greater than 0, and that's a rational number, then the limit as x approaches infinity of 1 over x to the r also approaches 0. And if you think about that, that really should make sense. let's say r is 2. Now it's 1 over x squared. Well, the denominator is just going to get bigger even faster than 1 over x did, so it's going to make it approach 0 even faster. Okay, the speed that this thing approaches 0 will eventually come back to us in much later sections, and we're going to need to understand that that's an actual key concept. And then also, if r is greater than 0, which is a rational number, the limit as x approaches negative infinity of 1 over x to the r is also going to approach 0. It's just going to mean that you're going to have 1 over an incredibly large negative number, which still approaches a y value of 0. All right, let's go ahead and do this first example. After we do this example, I'm going to let you know that you are most likely never going to use this specific method again in this class, because this is very tedious. You should be able to look at this and determine what the limit is just by looking at it. And that's going to eventually aid you when it comes to doing the math later on. If you look at the growth rate on the numerator and denominator, they both have an x squared as the highest power. So you should be able to look at the leading coefficients and know that our limit is going to be 3/5. However, there is an actual algebraic mathematical way that we show this. The idea is we need to take the limit as x goes to infinity, and we need to simplify this by dividing every single term, there's 6 terms on there, every single term by the highest power in the denominator, or the highest growth rate in the denominator, which in this case is an x squared. So we're going to divide every single piece by x squared. So I'm going to get 3x squared over x squared minus x over x squared minus 2 over x squared, all divided by 5x squared over x squared plus 4x over x squared plus 1 over x squared. Okay, this seems like it's incredibly long and it's a lot of writing, but this is the process. So then we're going to simplify what we can. So can't really evaluate the limit as it stands right here with all this stuff going on. So 3x squared divided by x squared simplifies to 3. X divided by x squared simplifies to 1 over x. And then 2 over x squared is just 2 over x squared. Divided by 5x squared divided by x squared is 5. 4x divided by x squared is 4 over x. And then 1 over x squared is just 1 over x squared. Now we can actually go ahead and use our limit laws and our theorems that we just said above. If we were to start taking the limits of each individual piece, now remember that you can literally split the limit on the numerator and denominator, then you could split up each individual piece. I'm not writing all that out. That would actually be even crazy for me. But you could do that. So we're just going to take the limit piece by piece here. And the limit of 3 as x goes to infinity, well, 3 itself is a constant. So the limit of a constant is the constant. So that's just 3. The limit of 1 over x, well, we just talked about that. The limit of 1 over x as x goes to infinity, I think was on this page. Yeah, limit of 1 over x as x goes to infinity is 0. So minus 0. The limit of 2 over x squared, well, it's a number over x squared. That is this limit law right here. 1 over x squared is no different than 2 over x squared because they're both going to go to 0 since the numerator stays constant. So minus 0. Same exact idea in the denominator. The limit of 5, it's a constant as x approaches infinity, is still 5. 4 over x is some number over x. Well, that's going to go to 0. And then 1 over x squared. Again, that's that theorem, which is 1 over x to the r power as long as r is greater than 1. Also goes to 0. So then you just simply end up with 3/5. That's a very, very long, drawn-out process to get something that we can just look at to understand where it comes from, but that is actually algebraically how you do it. All right, we are going to stop this video here. Even though I probably could finish this, I'm going to come back with another one that will definitely be less than 10 minutes, and we'll be done.